Hello, this is Dr. Huan. Today we are going to talk about limits. Specifically, we'll introduce the definition of the limits and then how to find limits graphically and numerically. Let's begin with the concepts of the limits. And here's the informal definition. We'll have formal definition later on. Suppose f is defined for all x near c except possibly at c. So what that means is, f doesn't have to be defined as c, but it should be defined on the x values nearby c. If the following happens, if f of x is arbitrarily close to L, and this L is a specific number, how close? As close to L as we like, by taking x sufficiently close to c. Well, x is you're making x close to c. It does not specify which side, so that means on either side of c, but not equal to c. When this happens, then we are gonna use this notation. This notation is read the limit of f of x when x is approaching c is equal to L. So practice how to read this a few times so that you can read this correctly. Now, what this is saying is we are interested in what happens when of f of x when x is getting closer to c. So the behavior, this behavior, we are going to call that a limit. If f of x is getting closer to a specific number L, then we are going to call this as the limit of f of x when x is approaching c. So the first question I would like to ask is, please, this definition, even though it is informal, it takes a little bit of time to fully understand. So I would encourage you to pause the video, read through this informal definition several times to understand it. And the first question that I have is, what's the difference between f of c is equal to L and the limit of f of x when x is approaching c is equal to L? So the difference lies on the first statement. Specifically talk about what happens when x is equal to c. What's the value of f? It is equal to L. This is what it says. It tells you nothing about the f when x is not equal to c. So you know nothing about f when x is not equal to c, okay? You only know when x is c, the function value is L. And the second one, the limits, this is telling you the behavior of f when x is approaching a specific x value c. The function, the y values, are approaching a specific number L. You have no knowledge about what function f is when x is equal to c. So in other words, you kind of know nothing about f when x is equal to c. You only know f is approaching L when x is nearby c, but nothing about f when x is equal to c. So there are two different things. Now with that, let's start with the next problem and use this problem to make sense of the limit graphically. All right, let's estimate the limits from the graph, okay? So first of all, let's take a look at this graph represents the function h, and then we're going to use the information provided in this graph to fill in or to answer all these questions. First of all, let's take a look at h of 2. So again, any time that you feel like you want to give a try first, please pause the video and think about it. So h of 2, that means what's the function value, what's the y value when x is 2? So let's read when x is 2, this little dot means the function h attains that value, which is 5, right? So which is 5, so we're going to write this is equal to 5. Now the second part of that is when x is approaching 2, how does h behave? So now let's take a look at from the graph. When x is approaching 2, so you know, a little greater than 2, and this is the function value. And then when x is getting closer to 2, and then we can see the function value is actually approaching these little open dots, right, from both sides nearby. So when x is approaching 2 from the left side, and we can see that the function value is really approaching this little open circle. So therefore we say in this case the limit of h when x approaches 2 is equal to 3. Okay, so again we don't look at what h value is when x is 2. We just want to look at the h value. What is that number that h is approaching when x is approaching 2 from either side of the 2? So which is this little open circle there, which is 3. So hopefully with this example that you begin to make sense of what limit is. It has nothing to do with the function value at that point. We just see the pattern, what value the function is approaching when x is approaching that specific value 2 in this case. Now take a look at the next point, h of 4. So h of 1, 2, 3, 4 is right there. And what is h of 4? Well, it's not defined at all because this is open circle, right? So therefore we say this does not exist. Does not exist, DNE. And then let's take a look at the limits of h of x when x is approaching 4. Again, we trace the graph from either side. When x is approaching 4 from either side, we trace this graph. So you see that from both sides, the y value, which is the h of the function h, it's approaching this open circle there, which is 1. So therefore we conclude that the limit is equal to 1 when x is approaching 4. Now let me erase those so that you don't get distracted there. Now let's take a look at next when h of 3, so 1, 2, 3, 3 is right there. This is 3. H of 3 is equal to, well, there's no open circle, so it's just right there, which is equal to 2. And the limit of x approaching 3 of h of x, what is that equal to? And then again, we try to look at from both sides and what this y value is approaching. It seems to me they're both approaching 3, right? Approaching the value y value 2. So therefore, the limit is equal to 2. Sorry, I kept saying 3 because x is approaching 3. This example actually shows some important idea here, which is about continuity that we will talk about in the near future. So I think it might be good to shed some light here now. So take a look at the first x value when x is 2. And we can see that the function is actually not continuous at 2 because there's a gap here, right? And then we can see that, okay, this function value is actually not equal to the limit at x equals 2, therefore there's a gap. And the second point, x equals 4, similarly, the limits exist, however, the function is not defined, therefore it's not connected, so therefore that's a discontinuity there. And the last point, x value x equals 3, and both function value and the limits, they exist and they're equal, and therefore it's connected. The function is connected over there. So actually in the near future, when we do the continuity check, we really have to look at what function value is and what limits is and compare them. When they're equal, then the function is continuous at that point. But that will be something that we'll talk about in the near future. So we don't want to focus it too much now. Well, I do want to make a note here. From this example, we can see that the existence or the non-existence of this function value f of x at certain point c has no bearing on the existence of the limit of f of x as x approaches c. So this is an important point to make. Whether limits exist and whether function value is defined or not defined, they have nothing to do with each other. So that's what we are trying to say. All right, so we talked about how to find limits from the graph. So usually this is pretty easy. You just look at the function value from both sides of the certain value c, and then if they approach the same value, then the limits exist, right? Now let's talk about how to estimate limits from a table. Let's consider this function f of x equals sine x over x. To sketch this graph, for values other than x equals 0, you can use standard curve sketching technique, and then you sometimes take enough points to plot into the xy plane and connect those points using a smooth curve, right? Now, at x equals 0, however, because it's not defined, it is not clear what to expect. Now we can create a table and make a conjecture on what happens when x is approaching 0. So therefore, let's pick enough points. This is the x value, this is my y value. Verify those y values for me using a calculator. When x is equal to negative 1.0, the y value plug in sine of negative 1 divided by negative 1. This is the y value, 0.84147. When x is equal to negative 0.5, so sine of negative 0.5 over negative 0.5 is going to be 0.95885. And when x is negative 0.1, and sine of negative 0.1 over negative 0.1 is 0.99833, and so on and so forth. So when x is negative 0.01, which is quite close to 0 now, it is equal to 0.99998. Well, of course, you can, if you want to see more what happens when x is even further close to 0, even more close to 0, you can pick some other points. X equals negative 0.001, right? And even 0.0001, etc. You can continue. Now, I believe that at the moment, I feel like I can see some clear pattern here now. So as x, if we can visualize, this is 0, and we first start with negative 1, and then plug in negative 0.5, and then negative 0.1, and then even negative -0.01, right? So these are the y values that we see. We do see that the y values are getting approaching 1. Now, and we, according to the definition, we have to look at x values nearby this c, which is 0 in this case, right? So we also have to look at the x values when x is approaching 0 from the this right side. What are the y values? So now, actually, because this function is actually even, sin x is odd, x is odd. When you have the ratio of two odd numbers, that's even. So therefore, the y values, actually, they're the same. When x is 1, it should be equal to the y value when x is -1, and so on and so forth. So therefore, we can see that those y values, when x is approaching 1 from the right, also approaching 1. That's what we observe. So therefore, based on those numerical values tabularized here, we can make a reasonable conjecture that this limit when x is approaching 0 is equal to 1. However, when x is 0, it's not defined because the 0 on the in the denominator that this value is not defined. So that's how we estimate the limits from a table. Well, sometimes these estimates here, it's a reasonable, and we have the faith that this is likely to be the case, right? So we just trust our conjecture at this moment. But does it always work using the table? We'll talk about it later. But for now, we see that that's what we observe. By the way, how do we actually verify that this is correct? I strongly encourage you at this point, after you make the table, make the conjecture, use your graphing calculator, make a graph of this sin x over x and see what happens. This actually is pretty interesting to see, but and then make sure that you feel like, okay, that actually when x is approaching 0, the y value is actually approaching 1. Now, let's talk about the next problem. So here you are given this problem. You need to find the limit of root of x plus 1 and then -1 divided by x. Okay, at the moment, you have learned two approaches. One, graphically. Second, estimate using those quantities from a table, right? Well, assume that you don't have a graphing calculator at the moment. You cannot graph. So what would you do? You just have to build a table just similar to what we just see here and begin to find the function value and make a conjecture. So this is the table that I would build. Again, pause the video if you would like to give a try first, which I would definitely strongly encourage you to try before you actually look at the answer. So I'm gonna, this is my function f of x, right? So I'm gonna say take some x value and then I'll evaluate the x value in this function, okay? And because here the limit that we are trying to find is when x is approaching 0. By the way, when x is 0, this is not defined because 0 on the bottom, right? So therefore, you cannot really take 0. Then we're going to take some x values nearby 0. So I'll just begin with -0.01, okay? And then I plug -0.01 into my calculator. So square root of -0.01 plus 1 minus 1 divided by -0.01, I got 1.99499. Okay, verify that for me. And now the next x value that I would like to choose. So again, what would you like to choose? Think about it and see if you will choose the same value as what I would choose. So I'll have to choose a value that's getting closer to x, right? So therefore, I'm going to choose negative 0.001, which is on the left side. So if this is 0, then the first value I chose was negative 0.01. And here this is a tenth of the previous one, so negative 0.001 now. So much closer to 0 than the previous one. And plug in the calculator, plug this value, x value, into, plug it into this function, and then use your calculator, evaluate it, and this is what I got, 1.99950, of course, more decimals there. And now make another, if you see a clear pattern, then I believe you can stop. If you don't see a clear pattern, then you should want to make another one until you see a clear trend. You see the trend. I feel like I believe that I see that it's getting closer to 2 when x is getting closer to 0. So I feel like I have enough. However, if you feel like, okay, I don't have enough, then you want to continue, just continue. So pick another one that's even closer to 0. And actually, this y value is 1.949 this time before a 5, okay? So the pattern is pretty strong to me, so I'm going to stop here. Now, this is not enough because we talked about when you find the limits, you have to look at x values nearby c, right? So nearby 0. Here we only look at the x values from the left side. We have to look at the x values from the right side as well. So therefore, I'm going to continue to choose x values. So this time, so this x value, this 0 is not defined, so I'll leave it. That's what we are trying to figure out, what would happen, right, when x is approaching 0. So now I'm going to say, let's pick 0.01. And when I plug in 0.01 in here, square root of 1.01 minus 1 divided by 0.01, I got 2.00499. And then similarly, you will have to choose the next value that's closer to 0, but from the right, when the first one I chose was 0.01, the next one I chose, I'm going to choose is 0.001, okay, 0.001. Does it have to 0.001? Can you choose 0.002? Yes, as long as getting closer to 0, that will be fine. Then the value that I have is 2.30 before a 5, okay? And then I'll continue to, I feel like I see the pattern already. I see the pattern. But just to be safe, I'm going to choose one more, 0.0001. And then plug in the 0.001 into this function. I get 2.40 before a 5, okay? So seems to me these values are approaching 2, getting smaller and smaller and approaching 2. From the left side, the values are getting larger and larger, but approaching 2 as well, right? So because of those numerical evidence, I'm going to make a conjecture this is going to be 2. Time for you to take out your graphing calculator and graph this function and verify visually that the limit is actually approaching 2. All right, so we've talked about 2 approaches, graphically and numerically. Now let's move on and take a look at some other scenarios, okay? All right, here the learning objective 2 is identify the ways that a limit fails to exist. Let's take a look at the following limits problems. So the first one, let me zoom in a little bit here. So the first one, we are going to look at this function, absolute value of x over x. So let's rewrite this. So first of all, absolute value of x. Actually, after you drop the absolute value sign, this is equal to x when x is greater than or equal to 0, right? When the value here is non-negative, you simply just drop the absolute value sign. When x is actually negative, to guarantee this, to guarantee that the absolute value, after the absolute value, the result is non-negative. So you have to add the negative sign. So negative of a negative value will guarantee to be positive. So this is how we drop the absolute value symbol. So therefore, this absolute value of x over x is actually can be equal to x over x, which is 1 when x is greater than or equal to 0, and negative x over x, which is negative 1 when x is less than 0. Now, if you make a little sketch for this function, when x is greater than or equal to 0, this is 1. And negative 1 when x is less than 0, like here, okay? When we look at the limits of this function when x is approaching 0, then let's take a look at that. Because we have to look at the x values nearby 0, right? So we have to look at the x value to the right of 0 and x value to the left of 0 and look at the y values. What y values are approaching. So on the right side, you can see the y values are remains 1, always remains 1. On the left side, the y values are remains negative 1. So no matter how close x is to 0, there's no a specific value y that this guy approaching. It's either 1 or negative 1. So there's no specific value f of x is approaching. For that reason, we claim that this limit doesn't exist. So I'm going to write this down so when x is approaching 0 from the right, f of x is approaching 1, right? So I'm not using the equal sign. I'm just using this arrow sign. Means it's approaching 1, because I don't talk about x equals 0. I just want to talk about when x is approaching 0. Now, when x is approaching 0 from the left, f of x is approaching negative 1. And no matter how close x gets to 0, there is no specific y value, right? Y value. F of x is approaching for that reason. This is the reason there's no specific value f of x is approaching. So the limit does not exist. Okay, so that's the first example that we looked at. The limit doesn't exist. Now let's take a look at the second one. Okay, the second one. Actually, let's take a look at the second one. I'm going to change this to 1 over x minus 2 squared at the moment. Okay, so instead of 1 over x minus 2, we'll consider 1 over x minus 2 squared when x is approaching 2. Now, if you make a graph of this guy, this graph is not too difficult to graph. It's just a horizontal shift 2 units to the right of the function 1 over x squared, right? So 1 over x squared, and you shift right 2 units, then you get to this 1 over x minus 2 squared, and which means the graph should look like this is the 2, and something like that, because 1 over x squared looks like this. Okay, you just shift this graph to the right 2. Now, when x is approaching 2 from the right, you can see the y value is going up indefinitely, and this x equals 2 is a vertical asymptote. It's not defined. Function value is not defined there. So, and then we can see that approaching infinity when x is approaching from 2 from the right, and similarly, when x is approaching 2 from the left here, the y value is also approaching infinity, right? So now ask yourself, is there a specific number, a specific y value that this function is approaching when x is approaching 2 from either side of the 2? If you say yes, the infinity. However, infinity just is not a specific number. It's actually there's no such a number called infinity. Infinity just represents that the y value is getting infinitely many large, right? So therefore, for that reason, we don't say that the limits, there's no limits. The limits doesn't exist. So let me quickly write this down. So from the graph, we see that when x is approaching 0, getting closer to 0, the y value is getting larger and larger, right? Larger and larger, basically infinity. So in fact, if you say, okay, how do you know that there's no such a specific large numbers that this y value is approaching? You can give a try. Just name any large number. I can always find a even larger y value, larger than the one that you name, when x is closer enough to 0. For instance, if you claim, say, y is 100, then I'll say when x is closer enough, like 0.1 away from the 2, the y value will be greater than 100. If you give me even larger value, I can always find a smaller x value close to 2, so that the y value is larger than the value you name. For instance, okay, if you give me, say, y is 100, now then I can claim then, as long as x minus 2 is less than 0.1, that means the x value is within 0.1, this range, about the 2. So in other words, suppose this is negative 1.9, this is 2.1. As long as x values are within here, then we can conclude this means x is less than 2.1, greater than 1.9. Then f of x, which is 1 over the x minus 2 squared, this value is less than 0.1, right? So that means this guy will be greater than 1 over 0.1 squared, which is 1 over 0.01, which is 100. So I can find some x values so that the y value is always greater than the y value that you name. So the idea is, regardless how big this y value you name, if you feel like, okay, there's a huge number that is the limit of this function, then I can always challenge that by finding another x value so that the y value is greater than the value that you name. So for that reason, we are going to say, so there is no such specific fixed y value, right? Y value f of x is approaching when x is approaching 2. Therefore, I can claim that limit does not exist. In fact, this is called infinite limits in the future, but it doesn't exist. Infinite limits is just describing its pattern. Okay, both sides it goes to infinity. All right, so this is the second example that we see here. Next, let's take a look at this one. This is an interesting one. The limit x approaching 0 cosine of 1 over x. Okay, actually cosine function is a even function, and then 1 over x, and cosine of the negative even function. So regardless the sign of this 1 over x, the result cosine of 1 over x will be the same. Now I do supply a graph of the cosine of 1 over x when x is approaching 0 from the right side. Again, this cosine function is even, so the left side will be the mirror image of the right side with respect to the y-axis. So we'll just take a look at this side. That should be sufficient. Now, if you want to say, how can I tell what value do you see that it's very difficult to see what this function is approaching when x is approaching 0? They're so dense, right? We just cannot zoom enough to see the line there. Now, so hard to see from the graph, right? Now we can actually try to convince you using a table. So I'm gonna just show you. So let's pick some special x values and then look at this y value. And let's say x is 1 over 2 pi. So let's do a little calculation. Cosine of 1 over x, and the x is 1 over 2 pi, which is equal to cosine of 2 pi, right? What is cosine of 2 pi? Cosine of 2 pi is the same as cosine 0, which is 1. And I'm going to choose 1 over 3 pi, next point, which is closer to 0. Now, this is 1 over 2 pi, is about 1 over 6.28. This is even closer to 0, right? And then cosine of 1 over 3 pi. X is 1 over 3 pi. This is equal to cosine of 3 pi, which is the same as cosine pi because cosine has period 2 pi. And cosine pi is actually -1. Now continue, 1 over 4 pi, even closer to 0, right? And then do a little, please use this as exercise. What is cosine 1 over 4 pi? Pause the video, do a little algebra. And here's the answer. It is actually 1 again, okay? And then 1 over 5 pi, closer to 0 now. It's actually -1, and you can probably imagine the pattern, okay? So these x values are approaching 0 from the right, okay, from the right, and 1, -1, and so on and so forth. And we can see that there's no specific fixed value when x is approaching 0. The y value is approaching. So I'm going to say, so no specific So this is the keyword, no specific fixed y value, f of x is approaching when x is approaching 0. I did not talk about it from the right side, but again, because it's even, it's definitely true when you change this to negative sign, okay? So therefore, I'll just say when x is approaching 0. Therefore, so this limit, the limit does not exist. Okay. All right. So I feel like these are pretty good examples to show you how limits doesn't exist. So generally speaking, some common types of behavior associated with non-existence of a limit. Number 1, f of x approaches a different number from the right side of c than it approaches from the left side. This is the first example that we saw. The y value is approaching 1 from the left and approaching negative 1 from the right, right? So in this case, the limit doesn't exist. Second one, f of x increases or decreases without bound as x approaches c. That's the second example that we saw. Number 3, f of x oscillates between two fixed values as x approaches c. So this is the third type that we see. Okay. Now I'm gonna close this section by asking you a question here. Can we actually trust the table? So far we have been looking, sometimes when we don't know how to find the limits, we rely on finding numerical evidence, and we based on the pattern that we observe, then we make a conjecture, right? So here I would like to present this particular problem, and I would like to invite you to create tables and then make conjecture, okay? So here's what we are looking at, this sign of pi over x when x is approaching 0. So when x is approaching 0, this guy definitely not defined, because when x is 0, this is pi over 0, is not defined, right? But we want to see the limit. How do we do that? We are going to create a table. You will take values of x closer and closer to 0 and see what value of the function approaches. So here, pick a number from 1 to 9, call it d, fill out the table. For example, if your digit is 3, okay, then you would compute sine of pi over, 0.3. The next one will be sine of pi over 0.03. Next one will be pi over 0.003, etc. So how about I'm going to start with this one. So let me look at the first one. So let's call this as d is 3, okay? So the first one is sine of pi over 0.3. So please use your calculator and verify the following result. I got somewhere around negative 0.8660, okay? And more digits over there. The next is 0.03. So therefore you compute sine of pi over 0.03. Do you see the x value is getting closer to 0, right? And this actually is equal to negative 0.8660 and many more digits. And if you compute the next one, sine of pi over 0.003, the value is about, so I should use approximately equal to, because there are many more decimals there, negative 0.8660, etc. Now, actually, if you continue to plug in smaller values and finding that, well, it's like that, okay? Now, pause the video and make a conjecture. Can I, based on this and then conclude that the limits when x is approaching 0 is equal to that value, some decimal value that starts with negative 0.8660 and so on and so forth. So think about it. If you feel like, okay, yes, that's sufficient evidence, then I would like you to change this d to some other value. For instance, I would like you to change to, say, 0.2, 0.02, 0.002, and so on and so forth. Okay, so in this case, calculate sine of pi over 0.2, sine of pi over 0.02, and so on and so forth. Okay, well, so do that, pause the video, do that, and let's compare the answer. So in this case, actually this is equal to 0, 0, 0, they're all zeros. So now can you conclude that, okay, it's approaching 0? Of course not, right? Because earlier we already see that when x is approaching 0, using these values, the y value is approaching some negative 0.866, and now when you use approaching 0 from using these values, is 0. So there's no specific fixed y value that the sine of pi over x is approaching. Therefore, we cannot claim that the limits, we can claim the limits doesn't exist, right? So now this is actually a pretty good lesson for you to see whether a table is trustworthy or not. That's why we always say estimate the limits using the table. So we call it estimates. Okay. Well, does that mean it's not useful? No, it will be useful. It gives you some good conjecture. In the later section, we'll talk about how to find limits analytically. That means using algebra approach. Okay, so this is the first part of the lesson. In the next lesson, I'll talk about the formal definition of limit.